Hi. So, in this module we will continue looking at classification and regression trees. So, in the previous module we looked at how to build the tree, right, but we never looked at when to stop. Right. So, if we continue growing a very large tree, so we might end up making a lot of decisions and essentially end up specializing your tree to individual data points. So, it will lead to overfitting of your tree to the data, and that is not a good place to be in. On the other hand, if you stop growing your tree too soon, right, you might miss out on finding interesting patterns in the data. Right. So, for example, the very famous XOR case, right. So, there is no single attribute on which you can split, right, and get any kind of improvement in your performance, because whether you split on x1 or whether you split on x2, so half your data is going to be positive, the other half is going to be negative, right. So, you really cannot hope to get any improvement by only splitting on one attribute. So, you just kind of stop that, saying that hey, there is no one individual attribute that gives me an improvement in performance, and therefore, let me stop. So, you might lose out on interesting patterns if you are going to stop too early, right. So, you cannot leave a tree that is very specialized to small data points, and you cannot stop early as well. So, what do we do? So, you typically grow the tree until you come to a point where there are few data points in the leaves. So, the leaf here would correspond to a region. So, I keep going the tree until I come to a point where each region has only a few data points. Typically, you would like to have about 4 or 5 data points at least per region, right. So, for using some of the standard tools, say something like Vika, so Vika actually stops by default when the number of data points in a region go down to 2. Okay. So, it will stop only at that point. That is still a significant overfitting, right. So, you grow a large tree, right, where there are very few points per region, and then you prune the tree. You basically start trying to collapse the internal nodes in the tree such that you come up with a better tree, right. So, we have looked at how you need a validation set. So, you have a training data and you have a validation data. So, one way of looking at pruning is to say that I will look at the performance of the tree on the validation data. Right. So, I look at the performance of the tree on the validation data, and then I will start collapsing some of the internal nodes of the tree. So, what do I mean by that? Suppose that I have a tree that, let us think of the tree that we had earlier, right. So, this is the tree that we had earlier. So, one way of pruning something like this could be to say that I am going to collapse one of the internal nodes, right, and replace it with a single region, right. So, there I have pruned the tree. So, this corresponds in the picture, this corresponds to doing something like right. So, that is R4 prime. So, now I can look at the performance of this pruned tree on the validation data versus the performance of the original tree on the validation data, right. So, now if there is not a significant dip in the performance when I have removed one of the internal nodes, then I will keep this new tree, right. So, that essentially tells me that whatever I did in terms of the previous test on T4 was something that was peculiar to the training data. So, when I look at it in the validation set, well, it really does not look like I need to make that split, right. Or on the other hand, there might be a slight decrease in performance, right, when I go from the original tree to the pruned tree. Okay. Now, the question you have to ask yourself is, okay, given the fact that I have reduced the size of the tree, okay, is it okay to pay the penalty in terms of that slight reduction in performance? Okay. So, there is this trade off, right. So, there is this what we would call the cost complexity trade-off. So, there is a cost that you incur in terms of the misclassification that or the misprediction in this case that you are going to make in terms of the reduction in the number of regions, and the complexity is essentially the number of tests that you have to perform and the size of the decision tree that you are operating with, right. So, this is the cost complexity trade-off, and depending on which side of the cost complexity trade-off that you want to be on, you can get more complex or less complex trees. Okay. So, there are many ways in which this kind of pruning techniques can be implemented, and one simple way is essentially to choose a validation set, right, and then have a trade off between the prediction error of the pruned tree in the validation set versus some measure of complexity of the tree. So, one measure of complexity of the tree is the number of internal nodes that you have in the tree, right. So, you can basically trade off the two and try to come up with a good smaller tree, right. So far we have been talking about regression trees, right. So far we have been talking about regression trees, and we looked at how we would split regions, right, and once having split found the regions, how do you fit what is the best prediction that you have to make in each of those regions, right. And how did we find the regions? We adopted a greedy approach by picking one variable at a time and then trying to find out which is the best point to split the variable, right. And we looked at the squared prediction error, and essentially now if you want to look at classification trees, if you want to look at classification trees, the only thing we have to ask ourselves is what is the appropriate measure that we will have to look at in the greedy search procedure, right. So, once we decide on what the appropriate measure is, so the rest of the framework that we need to build classification trees are already in place, right. So, we can do the greedy algorithm, and then once we know what is the appropriate measure that we are going to use, we can optimize that measure in the greedy algorithm, and we can use the same setup that we have for pruning. So, we have a validation data, and then we have a cost complexity trade-off, where the cost instead of being measured by the squared error is going to be measured by whatever metric we choose for a classification, right. So, I am going to say that I will build a classification tree where the prediction, so which we will call as p hat, okay, yes, okay. Right. So, p hat here is the probability that a data point in region M, okay, belongs to class K. Okay, the data point in region M, so one of these regions, okay, what is the probability that this data point belongs to class K. Okay. So, I am going to look at all the data points that fall in the region Rm, right. So, I am going to look at all the data points that fall in the region M, okay, and look at whether their class labels in the training data, whether it belongs to class K, right. So, if a point xi in region M, okay, if the label is K, right, then this will be 1. So, this summation is essentially going to count the number of data points in region M that belongs to class 1, right, or number of data points in region 1 that belong to class 2, and so on and so forth. This expression is for class K, right, and then I am going to divide it by the total number of points that fall in region M. So, Nm is the total number of points in region M. So, this essentially gives me an empirical estimate of the probability of a data point falling in region M belonging to class K, right. And if I am interested in actually returning the class label, then so the class in region M, right, is going to be Okay, so the class that I will assign to data points in region M is essentially that k that gives me the maximum p hat value. Okay. That makes sense. So, we look at the different error measures. That we can use. So, what is the most popular error measure in classification, or which is the most appropriate error measure in classification? Is a simple thing called the misclassification error. The misclassification error is given by right. So, the number of times the actual label, right, does not match the prediction that we make by our classifier. So, class M is the prediction made by our classifier in the mth region, right. So, for all the data points in the mth region, whenever the class label, the true class label does not match the predicted class label. So, I am going to sum it up, divide by the total number of data points in that region. So, this gives me the misclassification error, right. This for a specific region, and I can do this over all regions, and that gives me the total misclassification error. So, if you think about it, this is essentially right. So, the number of times this should have been correct is given by p hat m and the class that I am going to predict, right. So, this is given, this gives me the maximum from the previous expression that we had. So, the total misclassification error will be 1 minus p hat m. So, I can use this as my error measure. So, once I estimate p hat, once I estimate the argmax over k of p hat mk, then 1 minus that gives me the misclassification error for that region, right, and I can sum this over all the regions, right. But then there are a couple of slightly more common error measures that are used especially in the decision tree literature, right. So, one of these is called one of these measures is called cross entropy or deviance, that leads us to something called information gain measure for looking at the splitting criterion, right. So, the cross entropy is given by So, this is p hat mk is the label distribution that we have inferred. This is a label distribution that we have inferred from the data that was given to us. But if we stop and think about it, right, if you have sufficient training data, so that p hat mk is actually the true output label distribution as well, right. So, this cross entropy term actually gives us in some sense the amount of information that we need to encode the true label, given that you are in the region M. So, this gives rise to this measure called information gain, that tells us that okay, if I have not split into the following set of regions, how much information would I need to represent the labels of the data, versus having split into all these regions, how much less information do I need, right. If I do not know anything, right, about where the data point lies on this entire plane, right, then I have some amount of uncertainty about what the label is, right. Once I know that the data point lies in R1 or R2 versus the rest of the plane, I have less uncertainty about what the label should be, right. And so, given that when I have split the data, into 2 regions, I have gained some information about what the label should be, and that leads to this notion of an information gain measure, right. And so it comes from this cross entropy term, and we can use this also as a measure for splitting the tree in the greedy growing stage, right. Last one is the Gini index. It is given by the expression p hat m k into 1 minus p hat m k, and it is actually a measure of the disparity in the population of distribution of variables, right. So, if you think about it, so this is the probability that the label k appears in the distribution in a particular region M, and this is a probability that the label k does not appear in the distribution M, and this expression will be maximum when they are equally likely, right. The label k appearing and the label k not appearing in the region M are equally likely. So, that is really a bad situation for us to be in. So, in some sense, having a high value here essentially is a indicator that this is not a great way of splitting the data into different regions. So, when you could use any of these 3 measures in terms of growing your decision tree, and they have their own advantages and disadvantages, and so the cross entropy and the Gini index are more sensitive to node probabilities than misclassification rate, but then quite often we find that these lead to much better trees than using the misclassification rate directly. So, that brings us to the end of our discussion on classification and regression trees, but there are a few points that I would like to make about the use of tree based classifiers or regressors. So, the first thing is I glossed over a little bit the problem of handling discrete valued attributes. I said you could choose red or not red, but then if you think about a discrete valued attribute that has k possible values, you can see that there is a combinatorial many ways of dividing these attributes into 2 groups, right. So, you need to have a clever way of handling this, and then many of the decision tree packages do handle this in a meaningful way, right. The other thing which we have to be very aware of when you are dealing with trees is that trees are notoriously unstable. So, what do I mean by unstable is that if there is a very small change in the training data that you give to the trees, the tree that you build out of the data could be very different. So, you could delete a few data points and you might end up having a tree that looks very different. So, this is in contrast to some of the earlier things that we have looked at, like logistic regression or support vector machines, where these things are stable to deletion of 1 or 2 data points, but decision trees can be notoriously unstable. So, one way that people get around this problem of instability in decision trees is to make sure that you build many different decision trees, right, with slightly different views of the data, and then combine the predictions made by all the decision trees into a single tree. Okay. So, that way we can actually make sure that the classifier that you build, the overall classifier that you build, is reasonably stable. And another point that we have to look at, suppose you are fitting decision trees using regression. So, you can see that for each region we will be outputting a specific constant value, right. At no point are we worried about how will the value change from R1 to R2, right. So, we are only worried about what is happening in R1, and we are fitting a value in R1, and therefore, there is no concern of smoothness in our fits, right, and therefore, the fit that is given by a decision tree can be pretty non-smooth, right. So, if smoothness is a criterion, then we will have to either add some more regularizing factors into decision trees, which makes it more complicated, or we will have to look at other forms of regressions, right. So, just keep in mind, so decision trees are very powerful classifiers, very powerful regressors. They are wonderful in terms of interpretability, but they also come with their own caveats. See you later.